Look at this severely polluted river. Our cities pump millions of gallons of toxic wastewater into waterways like this every single day. But the ultimate weapon to clean up this massive environmental disaster might just be microscopic. How can microscopic life systematically erase massive amounts of pollution? That is the promise of bioremediation. To clear that nutrient-overloaded wastewater, you start by dropping in a single microscopic cell, 𝘊𝘨𝘭𝘭𝘢𝘳𝑚. As it floats in the darkness, it actively pulls in those toxic nutrient particles, absorbing that pollution to directly fuel its glowing green chlorophyll structures. As the cell consumes these pollutants, it rapidly divides, multiplying into a dense green biomass. This population explosion literally eats the contamination, visibly transforming the cloudy wastewater into perfectly clear water. But you can't just drop wild algae into a river and expect a miracle. A cell's biochemical strength and growth speed are dictated entirely by its initial laboratory diet, a highly specific baseline nutrient recipe known as its growth medium. So before they can clean rivers, scientists test different media recipes in a head-to-head laboratory competition. The competitors are 4 standard flasks: BBM, BG11, M8, and modified BG11. So if our ultimate goal is to cultivate the absolute strongest algae to clear that polluted wastewater, which of these 4 growth media must it conquer first? Let the experiment begin. How do researchers physically figure out the recipe to turn pond scum into a tank of gas? They follow a strict step-by-step map to deconstruct the process. It starts by growing a specific strain, 𝘊𝘨𝘭𝘭𝘢𝘳𝑚, in a lineup of liquid nutrient broths. They test these chemical diets under precise light and temperature controls. Next, they measure the yield. First, they filter and bake the algae dry to get an exact physical weight. Second, they test exactly how much light the green culture blocks in the water. But raw weight isn't fuel. Scientists need to access the oils locked inside the cells. By adding chemical solvents and spinning them rapidly, the algae separates, leaving a distinct layer of pure extracted oil. That extracted oil is finally heated with specific acids and alcohols to strip away unwanted parts. What's left behind are the precise fatty acid molecules that make up usable biodiesel. And by tracking every single step, they discovered a counterintuitive secret. The diet that grows the most algae isn't the best for fuel. You actually have to starve them of nitrogen to force them to hoard oil. How do researchers place a sample of 𝘊𝘨𝘭𝘭𝘢𝘳𝑚 into a controlled laboratory flask? They prepare 4 different chemical diets, or growth media, and sterilize the equipment. After inoculating the flasks, they cultivate the algae for 12 straight days. They measure biomass and lipids, revealing a massive trade-off. The fastest-growing algae have the lowest oil content. Take the nutrient-rich BG11 diet. High phosphorus levels trigger the biomass pathway, massive population growth, but barely any fat. But the bold basal medium diet triggers the lipid pathway. Once the algae consume all the nitrogen, they can no longer divide to reproduce. Instead, the trapped cells pivot their metabolism to stockpile energy, filling their walls with dense lipids. So instead of just farming a massive green swamp, by intentionally starving these cells of nitrogen, researchers force them to transform from simple plants into dense, microscopic biofuel factories. So let's look at 4 𝘊𝘨𝘭𝘭𝘢𝑚 algae cultures competing for the highest yield. The measurement mechanism is brilliantly simple. A targeted beam of light shines directly through a transparent sample flask. But the light doesn't travel through empty liquid. It crashes into the physical algae cells, causing the primary beam to scatter and dim. This reveals the core rule of optical density. The less light that survives the journey to the sensor, the higher the numerical score, which translates directly to a higher concentration of biomass. Apply this to our lower-performing samples, like M8. More light successfully passes through their thinner liquids, keeping scores low. But BG11 is the darkest medium. Its incredible cell density blocks almost all the light, achieving the highest peak score of 3.408. With this massive winning density, the BG11 culture is now ready for its real-world job. It is fully equipped to filter heavily polluted wastewater, turning toxic gray environments into crystal clear blue.